Welcome to our bioprocess engineering online tutorial, Microbial Kinetic Analysis and Continuous Fermentation on Spreadsheet. Through the bioprocess engineering online tutorials, you learn the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, visit us at bioprocessdigital.com. You also learn how to use spreadsheet software for key bioprocess engineering tasks, including analyzing experimental results, modeling and simulating bioreactors, designing and optimizing bioprocesses, evaluating economic and environmental performance. Microbial kinetics are conventionally determined through batch fermentation experiments. In a previous tutorial, we described the determination and analysis of microbial growth rates in batch fermentation using a spreadsheet-based approach. In this tutorial, you will use a spreadsheet to analyze the experimental kinetics of microbial fermentation operated in continuous mode. You will learn why continuous fermentation is used, how to calculate microbial rates during continuous fermentation, how to characterize microbial fermentation kinetics. Microbial kinetic studies are usually performed in batch fermentation experiments. These experiments help determine important biological rates, such as substrate consumption, especially of carbon sources like sugars, cell growth, metabolite or recombinant protein production. In batch fermentation, cells are typically exposed to high sugar concentrations at the start of the process, often in the tens of grams per liter range. Only toward the end of the fermentation are cells briefly subjected to low sugar concentrations as the available substrate becomes depleted. In addition to analyzing microbial kinetics at relatively high sugar concentrations, it is also highly valuable to investigate cellular activity under prolonged low sugar conditions. When cells are exposed to sustained low sugar concentrations, their growth rate decreases significantly. However, this change in nutrient availability can also lead to major metabolic shifts. For example, there may be a considerable reduction in the production of growth-associated metabolites, such as ethanol, acetate, or lactate. Conversely, there may be a marked increase in the synthesis of non-growth-associated metabolites, such as antibiotics or other secondary metabolites. Continuous fermentation provides an effective way to study these phenomena, as it allows the cultivation of microorganisms under controlled and steady low substrate conditions for extended periods. The kinetic analysis of continuous fermentation is illustrated here, using the case study of baker's yeast, Saccharomyces cerevisiae. When cultivated in a batch fermentation under aerated conditions with an initial glucose concentration of 50 grams per liter, the process typically yields about 7 grams per liter of yeast biomass after 8 hours of growth. During this time, approximately 8 grams per liter of ethanol is also produced. The ethanol excretion occurs as a result of overflow metabolism, where the excessive sugar flux through the yeast glycolytic pathway surpasses the capacity of the respiratory system, leading to the formation of ethanol, even in the presence of oxygen. Yeast production in continuous fermentation is carried out as follows. The process begins with a batch fermentation, where the fermenter initially contains 1 liter of medium with 5 grams per liter of glucose. After 4 hours of batch growth, continuous operation is initiated by starting the feed of fresh medium, also containing 5 grams per liter of glucose, at a flow rate of 0.3 liter per hour. Simultaneously, an equal flow rate of culture broth is withdrawn from the fermenter. During the initial batch phase and the subsequent continuous operation, the yeast fermentation shows the following trends. The glucose concentration gradually decreases and stabilizes at a steady-state value of about 0.3 gram per liter. The biomass concentration continues to increase, although at a slower rate than during the batch phase, eventually reaching approximately 2 grams per liter. The ethanol concentration rises during the batch phase, reaching a maximum of around 1 gram per liter, and then declines steadily during continuous operation to about 0.2 grams per liter after 24 hours. These results indicate that under continuous glucose-limited conditions, yeast metabolism shifts from overflow, ethanol producing, to fully respiratory growth, reflecting a more efficient use of the carbon source. The kinetic analysis of continuous fermentation aims to address the following key questions. Which specific rates should be determined? How do these rates change during continuous operation? What is the relationship between the rates of cellular growth and metabolic activity? By answering these questions, we can gain a deeper understanding of how microorganisms regulate their metabolism under steady-state conditions, and how growth and metabolite formation are interconnected. When analyzing the kinetics of a microbial fermentation, two types of rates are determined. First, the microbial specific rates. These rates characterize the metabolic activity of cells during the fermentation. For growing yeast cells, the key specific rates are the specific rate of glucose consumption, Q-GLU, measured in grams glucose consumed per gram cells an hour. The specific rate of yeast growth, mu, measured in gram cells produced per gram cells an hour. And the specific rate of ethanol production, Q-ETH, measured in gram ethanol produced per gram cells an hour. The second type of rates are the volumetric fermentation rates. These rates express the intensity of the fermentation process within the fermenter. For the yeast fermentation, the key volumetric rates are the volumetric rate of glucose consumption, R-GLU third, measured in grams glucose per liter per hour. This rate is the product of the specific glucose consumption rate, Q-GLU, and the concentration of cells X. The volumetric rate of cell growth, Rx third, measured in gram cells per liter per hour. This rate is the product of the specific growth rate, mu, and the concentration of cells X. The volumetric rate of ethanol production, Rth third, measured in grams ethanol per liter per hour. This rate is the product of the specific ethanol production rate, Q-ETH, and the concentration of cells X. How are the microbial rates calculated from the experimental results of the continuous fermentation? The rates of yeast growth, ethanol production, and glucose consumption are determined from the experimentally measured time variations by applying instantaneous mass balance relations to the respective fermentation components. For a fermentation component, the instantaneous mass balance on the fermenter that expresses the fundamental principle of mass conservation at each instant is written as inlet rate plus or minus production rate equals outlet rate plus internal variation rate. The second production rate term is positive for the produced biomass and metabolite, negative for the consumed sugar. During continuous fermentation, the culture medium is fed and withdrawn at a constant flow rate Q liters per hour, while the working volume V in the fermenter is maintained constant. For growing yeast cells, the instantaneous mass balance, in grams cells per hour, is expressed as production rate, Rx third, V equals outlet rate, Qx, plus variation rate, dVx over dt. Thus, the volumetric growth rate, Rx third, is calculated as Rx third equals Q over V, x plus dx over dt. The specific growth rate, mu, in our -1, is then calculated by dividing the volumetric rate, Rx third, by the cell biomass concentration x. Similarly, for the excreted ethanol metabolite, the instantaneous balance in gram ethanol per hour is expressed as production rate, Re third, V equals outlet rate, Qth, plus variation rate, dVth over dt. Thus, the volumetric ethanol production rate, Re third is calculated as Re third equals Q over V eth plus D eth over dt, and the specific ethanol production rate, Q eth, in gram ethanol per gram X per hour, is then calculated by dividing the volumetric rate, Re third, by the cell biomass concentration X. For the consumed glucose, the instantaneous glucose balance, in gram per hour is expressed as inlet rate, Q glue feed, minus consumption rate, R glue third, V equals outlet rate, Q glue, plus variation rate, dV glue over dt. Thus, the volumetric glucose consumption rate, R glue third, is given by R glue third equals Q over V, glue feed minus D glue over dt. The specific sugar consumption rate, Q glue, is then calculated by dividing the volumetric rate by the biomass concentration. The yeast continuous fermentation kinetic analysis is carried out on a spreadsheet that contains the following sections: the experimental results table with the measured yeast, ethanol, and glucose concentrations during the continuous fermentation, the fermentation and cellular rates calculation section, and the yeast rates analysis section. To calculate the volumetric rates of yeast growth, ethanol production, and glucose consumption, it is necessary to evaluate the time derivatives of the corresponding concentrations during continuous fermentation. In practice, these derivatives can be conveniently obtained in a spreadsheet using numerical differentiation techniques. The time derivatives of the biomass, metabolite, and substrate concentrations can be estimated by fitting smooth curves through the experimental data. For the yeast biomass concentration, for instance, the variation in cell concentration with time is well represented by a third-order polynomial function, x equals at cubed plus bt squared plus ct plus d. The corresponding time derivative is then obtained analytically as dx over dt equals 3at squared plus 2bt plus c. A similar approach is applied to determine the time derivatives of ethanol and glucose concentrations. In the cellular growth rate section, you first determine the third-order polynomial curve that best fits the experimental cell concentration variation. The procedure is the following. On the biomass concentration graph, add the trendline third-order polynomial curve through the experimental points and display the curve equation. Report the values of the polynomial parameters a, b, and c. The yeast growth rates are then determined as follows. With these polynomial parameter values, calculate the time derivative of the cell concentration as dx over dt equals 3at squared plus 2bt plus c. Determine the volumetric growth rate Rx third as Q over Vx plus dx over dt. Finally, calculate the specific growth rate mu as mu equals Rx third divided by x, and graphically display its time variation. In the ethanol production rate section, you first determine the third-order polynomial curve that best fits the experimental ethanol concentration variation. On the ethanol concentration graph, add the trendline, third-order polynomial curve through the experimental points and display the curve equation. Report the values of the polynomial parameters a, b, and c. The ethanol production rates are then calculated as follows. With the polynomial parameter values, calculate the time derivative of the ethanol concentration as d eth over dt equals 3at squared plus 2bt plus c. Determine the volumetric ethanol production rate R eth third equal to Q over Vth plus deth over dt. Finally, calculate the specific ethanol production rate, Q eth, as R eth third divided by x, and graphically display its time variation. In the glucose consumption rate section, you proceed in a similar way to first determine the third-order polynomial curve that best fits the experimental glucose concentration variation. On the glucose concentration graph, add the trend line, third-order polynomial curve, through the experimental points, and display the curve equation. Report the values of the polynomial parameters A, B, and C. The glucose consumption rates are then calculated as follows. With the polynomial parameter values, calculate the time derivative of the glucose concentration as d-glu over dt equals 3at squared plus 2bt plus c. Determine the volumetric glucose consumption rate, R-glu third, equal to Q over V, glu feed minus d-glu over dt. Finally, calculate the specific glucose consumption rate, Q-glu equals R-glu third divided by X, and display its time variation. Based on the observed time variations in the specific rates of yeast growth, ethanol production, and glucose consumption during continuous fermentation, several conclusions can be drawn regarding the kinetic behavior of the yeast. The yeast exhibits similar temporal trends in its specific rates of growth and metabolism. The highest specific rates are observed at the end of the initial batch phase. During the continuous phase, these specific rates gradually decrease. The specific rates of glucose consumption and biomass formation show only slight decreases before reaching steady-state values. In contrast, the specific ethanol production rate declines more markedly and approaches zero over time. The pronounced reduction in ethanol production during continuous fermentation can be best characterized by calculating the stoichiometric coefficient YF over X, expressed as grams of ethanol produced per gram of biomass formed. This coefficient is calculated as the ratio between the specific ethanol production rate, QF, and the specific growth rate, mu. YF over X equals QF over mu. It is observed that YF over X decreases progressively during the continuous fermentation, from approximately 1.5 to nearly zero. This decline in YF over X correlates with the reduction in glucose concentration observed during continuous operation. Under glucose-limited conditions, yeast metabolism shifts toward growth rather than fermentation, leading to a lower ethanol to biomass stoichiometric yield. The metabolic shift of yeast toward growth rather than fermentation is well characterized by the biomass yield coefficient Yx over glu, expressed as grams of biomass produced per gram of glucose consumed. This coefficient is calculated as the ratio of the specific growth rate mu to the specific glucose consumption rate Q-glu. During continuous fermentation, Yx over glu increases from approximately 0.2 to 0.45. This increase in Yx over glu correlates with the progressive decrease in glucose concentration observed during the continuous phase. Prolonged glucose limitation enhances the efficiency of glucose conversion into biomass. The kinetic analysis of continuous fermentation reveals the metabolic transition in yeast when grown under glucose-limited conditions. During the batch phase, yeast operates predominantly in a fermentative state. At high glucose concentrations and high growth rates, excess glucose flux leads to metabolic overflow and significant ethanol production. This phase is characterized by a high ethanol to biomass yield coefficient, YF over X, and a low biomass to glucose yield coefficient, YX over glu. In contrast, under glucose-limiting conditions during continuous operation, yeast shifts to an oxidative metabolic state. Ethanol production is markedly reduced or completely suppressed, while the efficiency of glucose conversion into biomass increases. This oxidative state is characterized by low YF over X and high YX over glu values. In this tutorial, you learned how to use a spreadsheet to analyze the kinetics of a continuous microbial fermentation. Continuous fermentation is an excellent approach for investigating microbial behavior under prolonged, low substrate concentrations, conditions that are difficult to maintain in batch systems. Using instantaneous mass balances, both volumetric fermentation rates and specific microbial rates can be calculated in a spreadsheet by applying numerical derivatives to the measured concentrations. This kinetic analysis reveals how microbial activities change over time as the sugar concentration decreases. It also allows you to determine the stoichiometric coefficients, describing how sugar is converted into biomass and into excreted metabolites. Altogether, continuous fermentation provides a powerful framework for understanding the metabolic strategies of microorganisms under steady, substrate-limited conditions. If interested, you can gain a deeper insight in microbial fermentations by enrolling to one of our 2 online courses, Digital Scale-Up and Optimization of Microbial Fermentations, and Simulation, Scale-Up and Optimization of Fermentation Processes. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.